Hello everyone, welcome back to Calculus BC. In this lesson 36, we're going to talk about logistic growth. One thing I want to say about logistic growth is we've actually already done something very similar to this called exponential growth, where we actually have this equation that we talked about, that the change in population with the rate of time is equal to some proportionality constant times the population. And then we did our solving, we separated our variables, we solved the equation, and we got the function that p is equal to our initial, which we've called a, e to the kt. And so this is if we have no bound in our growth. So today, in this lesson, the logistic growth, we're going to talk about what happens when we actually have bounds. So a very classic example of when we would use this is population in the world. So as population grows, and you guys know that it grows pretty fast, as we go through time, it's gotten much bigger, it's grown faster. The population from like 1980 to now 2021 is really crazy, but there's got to be a moment. There's got to be a moment where the population has to level out. We can't just keep having our population go on and on and on to the point where we overpopulate the world. So this, like I said, is an example of where we actually have some upper bound that we have our curve to be. And we're going to denote this in this lesson as L, and we're going to call this what we call our carrying capacity, So this is going to be the upper bound that you guys would see here. And so let's go to the bottom here and talk about, well, what's the equation look like? So if we don't have a bound, we've actually looked about exponential growth here, dp over dt equals kp. Well, if we actually have a bound, then you guys will see here's our new formula, where k is still the constant that we talked about previously. This is going to be a population, and then it's going to be times 1. This is going to represent 100%. This is the highest it can be, minus the population over the carrying capacity. And so let's actually look at this. Now, if we were to separate these variables, right, because the whole point is we want to actually get the equation that we can start plugging stuff into. So if we separate our variables, I'm not going to show you guys that on this video because here is the math for it. And it's not challenging. It's not challenging, but it's very tedious. And there's no reason for me to go and discuss all that. But what ultimately comes out of it is this right here, this equation that we want to use. So we want to use the equation that population is always going to be equal to our carrying capacity. Again, this is going to be the maximum amount that we can have all over some constant a that we're going to figure out how that is equal to, times e to the negative kt, and then we're going to do the plus 1. We're going to do plus 1 to it. So let's actually look at the next page and say, okay, well, what will we use? So we have now derived from this differential equation our equation that will give us population when we have a restriction. And so I just write it out like this. I like to have the 1 in the front. I don't really know why, but this is going to be the equation that we're going to use right here. So carrying capacity all over 1 plus a e to the negative kt. And just like in the exponential growth problems, we're given information to basically help us find what the a value is and what the k value is. And that's exactly what's going to be happening here. We're going to figure out how to find the a and the k, and then we're going to use that equation to figure out any other information that we need to do. So one really cool thing about that is if we look at the initial, so if we make our time equal 0, and you're using this equation right here, if we make time equal 0, because again, what is a? And we talked about this in the exponential growth. A has been represented as an initial value, right? We talked about that. So a is going to represent our function. We have an initial population. So when time equals 0, then we're going to have p of 0 here. We're going to make e to 0. Time is going to be 0, so this is going to go away. And then we're going to come up with an equation for a. All right, a is not going to be equal to the initial population in this case. It's going to be equal to the carrying capacity minus whatever the initial condition is, all over the initial condition. And it's just solved based on the fact that we have this equation right here. And you guys can see the simple math for that. So let's actually solve the problem. Let's do a couple of these problems knowing this equation right here. So I'm going to go ahead and just write it down one more time for us so we can reference it. And then we're going to solve this problem with this series of questions for this first problem. All right, so here are the equations that we're going to use. It says find the solution to the initial value problem that we see right here. And given that P of 180, so the population at 180 is 200, where T is given in years since 1980. All right, so years since. So we want to know that t equals 0 for the population of this. So our initial time is going to be at 1980. So we know that the 200 is going to be represented as p is of 0, right? So this is going to be the population at time equals 0. The other thing that we can look at using this equation is that we know that we know that the k value actually is going to be negative 0.01, because k is going to be negative in our equation. And we also know that this is going to be our L, so our carrying capacity is going to be L. So just looking at the equation itself, we were able to identify what p sub 0 is and what L is. Actually, what k is and what L is. So now let's figure out how to find A. Now, again, we can find A by just taking into the equation of the carrying capacity, which is going to be 500, which is going to be given to us right here, minus the initial population. Well, our initial population is going to be 200 all over 200. And so we're going to get this as 300 over 200, and we're going to simplify this down as 3 over 2. So what this does for us, ladies and gentlemen, is the fact that we can now rewrite our function that we're going to have here, and we can start plugging stuff in. So we know that L is going to be 500, again, given to us right here in our equation. We know that A is now going to be 3/2 e to the negative kt. And so this is a step forward to get us the general formula for this particular problem. So now what we need to do is figure out what our k value is. So we got to actually figure out what k is going to be here. Well, we already know what k is, right? We already know what k is. K is given to us right here. So we can actually now erase this little piece and say that k is going to be 0.01 t. So we now have the equation that we need to find out the next part of these problems. So question number, well, let's just say this part right here. Use the equation to find the population in 1985. Well, guys, all this is really asking us to do is find the population when time equals 5, right? Because t is represented in years since 1980. So we're going to use p of 5. So we are going to use our calculator, and we're just going to take the equation that we have. Again, here's our carrying capacity. This is always going to be 1. We found our A very simple by using the formula, again, that we have right here. We have E that we found from our equation, and then we're going to multiply this by 5, and then we're going to use our graphing calculator to find out that this is going to be 206. So population 1980 is 200. This is probably maybe in millions. And now this is going to be 206, again, probably in millions. The next question asks, when does the population reach 450? So this one, again, very practical to what we've done before. This is asking me, okay, what time t do we get 450? 450. So we're going to set our equation equal to 450, and now we're going to solve for our t value. We're going to solve for our t value. And so in this one, we're going to cross multiply, right? So we're going to get 450 plus, and then again, 2/3 or 3/2 of 450 is going to be 675 e to the negative 0.01 t, and we're going to set that equal to 500. We're going to go ahead and subtract 450 from 500. So again, without having to write everything down again, I'm going to go ahead and subtract 450 from 500, and I should just erase that 1 0, right, because it's going to be 50. I'm going to now divide by 675, and again, this is a calculator question, like so, and then we're going to implement the natural log to both sides. The natural log of e to the negative 0.01 t is equal to the natural log of 50 over 675. This is now going to cancel. That's going to leave us with negative 0.01 t on the left-hand side equals to the natural log of 50 over 675. When we divide both sides by negative 0.1, we're going to get that t is going to be equal to 260. Now remember, that's not the question that was asked. The question is when? When does the population reach 450? So we know that in 260 years, it's going to reach 450. And again, I'm assuming this is in millions if we look at the context of the problem. Well, so we're going to take 1980, which is originally what we had. So we're going to take 1980, and we're going to add 260 years to that. And then when we do this, we're going to get 2240. So in 2240, our population will be 260, or probably 260 million. The last part of this question is asking what population when the population is growing the fastest. So first thing I'm going to tell you guys what to do here is you're going to go back to your differential equation that was given to you at the very top of the page. So I'm just rewriting this down here. And then I'm going to simplify this. I'm going to simplify this by distributing my 0.01p. So this is going to be like this. And what I'm going to end up doing, and why I decided to do it this way, is I want to find the derivative of this. Because remember, if we want to know when it's growing the fastest, we want to know when the rate of change of our differential equation is actually going to be the largest. So we want to find like an absolute max, right? So this question is really going back to an absolute maximum of our differential equation. So whenever you guys are asked to find when the population is growing the fastest, you're going to find your second derivative. And so you're going to go ahead and let me change the color up here for us. So you're going to find your second derivative because that's really important for what we're going to do. And so I'm going to go ahead and be left with, well, 0.01. Here's our easy one. And then when we move the 2 down, we're going to have 0.01 over 250 p. And so we're going to set this actual equation equal to 0, right? Because again, how do you find your absolute max or min? Well, you find your derivative of your function, this is our rate, and then we're going to set it equal to 0. And then we're going to use our calculator to graph this. And if you graph this in your calculator and you look at the max of this, and you guys can do this on your own, you can trust me with this, you're going to find that p is going to be equal to 250. So this is saying that when the population is at 250, probably again million, that's when our population is going to go the fastest. Another thing that I'm going to tell you guys that's really awesome about these type of questions is, and this works all the time, this is going to be amazing, is that you actually don't have to do this method, because the answer to this question always is going to be half of the carrying capacity. So whatever L is, you divide it by 2. And that's exactly what you guys do. If you graph this in your graphing calculator, you're going to find that you're going to have a maximum at 250. Well, our carrying capacity in our problem was 500. And so the answer for this is going to be just divided by 2. So it actually is really awesome that it works out like that every single time. Every single time. All right, so that is all I have for you guys for this video. We're going to come back and do a couple more examples of logistic growth, and I'll see you guys in the next video.